A critical characteristic of any measurement instrument is its accuracy. In other words, how closely the instrument's reading reflects the true value being measured, with a minimum of uncertainty. The lower the uncertainty, the more confidence we have that this reading is accurate and reliable. Unfortunately, the relevant specifications for electrical measurement equipment are often expressed in terms unfamiliar to less experienced users. For instance, the specs for a digital multimeter may list its uncertainty for measuring DC voltage as plus or minus 0.2% plus 2 counts, with no further explanation about what this formula means and how it can be applied to the displayed reading. This can make it difficult to compare the accuracy of different products, or even know whether or not a particular instrument is suited to your requirements. This video describes how to determine accuracy for electrical measurement instruments. We define terms such as digits, counts, resolution, uncertainty, and error. We also explain the importance of selecting the right measurement range when taking a reading. In this video, we use a digital multimeter as our demonstration instrument. However, most of what we'll cover also applies to other types of instruments. Two terms critical to understanding accuracy are digits and counts. It's important to note that neither term defines accuracy. Instead, they define an instrument's resolution, a point we'll discuss shortly. Resolution is a key factor in calculating accuracy and uncertainty, so we need to clearly understand these concepts. Digits defines the number of digits an instrument can display. For example, a 4-digit multimeter can display 4 0 through 9 digits. This fairly simple concept becomes more complex when the leftmost digit, usually called the most significant digit, cannot display the full range of numbers. For example, a so-called 3.5-digit instrument can display either a 1 or 0 as the most significant digit. Thus, the highest reading this multimeter can display within a single measurement range is 1999. Readings greater than this must be displayed in a higher range, if available. For instance, a reading of 20 volts could be displayed as 020.0 volts, with a decimal point shifted 1 digit to the right. This is further complicated when the most significant digit can be numbers other than 0 or 1. There is no uniformly adopted standard for expressing this as a fraction. For example, a 3 3/4 digit multimeter typically refers to an instrument whose most significant digit can be 0, 1, or 2. But this fraction is also used on occasion for instruments that can display 3, 4, or 5 as the most significant digit. To minimize this confusion, many manufacturers now describe their products in terms of counts rather than digits. Basically, this defines the number of different readings the instrument can display within a measurement range. For example, the 3.5-digit multimeter described earlier is a 2000 count instrument, since it is capable of displaying readings to plus or minus 1999. The value of each count is determined by the reading's rightmost number, called the least significant digit. In the preceding example, for a reading of 19.99 volts, each count equals 1/100th of a volt. For a reading of 20 volts, each count equals 1/10th of a volt. Therefore, an instrument's measurement range can significantly impact accuracy, as we'll discover later in this video. Users often refer to resolution and accuracy interchangeably, but it's important to understand the distinction between these terms. Resolution defines the smallest possible measurement change the instrument can detect. Thus, a 1000 count digital multimeter can display a change of 1/1000th of a unit, while a 10,000 count instrument can detect 1/10,000th, in other words, 10 times the resolution of the 1000 count multimeter. And since resolution depends on the size of each unit, the smaller the better, the lowest possible measurement range should be selected when making high-resolution readings. However, these numbers say nothing about an instrument's accuracy. The 1000 count digital multimeter may have a measurement uncertainty much smaller than the 10,000 count model, and therefore produces more accurate readings. Although resolution is a critical factor in calculating uncertainty, it is not the sole factor. A second factor in calculating uncertainty is expressed as a percentage. Recall our previous example specification of plus or minus 0.2% plus 2 counts. This indicates that the total uncertainty is 2 counts plus a percentage of a value. This can be a percentage of the reading or a percentage of the instrument's range. Uncertainty can be significantly affected by which of these values, reading or range, is used in the calculation, since the reading is generally much smaller than the range. For example, consider a 1,000 count digital multimeter displaying a reading of 100 volts. 1% of the reading would be 1 volt, while 1% of the range would be 10 volts. So be sure to check whether the percentage applies to the reading or the range when comparing specifications of different digital multimeter models. Note that the uncertainty specifications for all AEMC instruments are always expressed as a percentage of the reading. Now let's apply what we've learned. We've hooked up a 6,000 count multimeter to a battery. This instrument features an uncertainty specification of plus or minus 0.2% of the reading plus 2 counts when measuring DC voltage. With the range at the lowest setting, we get a reading of 5.000 volts. We start by deriving 0.2% of the reading, or approximately 0.01 volt. We then add 2 counts. Taking the least significant digit of our reading, we define each count as 1,000th of a volt. Thus, the sum of the 2 counts equals 0.002 volts. Adding the percentage and counts together, we calculate an uncertainty of plus or minus 0.012 volts, or 12,000ths of a volt. Thus, in the example shown on the screen, the actual value falls within the range of 4.988 to 5.012 volts. This calculation highlights the importance of selecting the optimal measurement range. To demonstrate this point, watch what happens as we change the multimeter's range to plus or minus 59.99, 599.9, and finally 5,999 volts. Notice the decimal point moves to the right with each change of range. This indicates an order of magnitude increase in a least significant digit, and as a result, a commensurate increase in the value of 1 count. At the highest range, the reading is 0005, with 1 count equal to 1 volt. Applying the formula, the uncertainty in this case would be approximately plus or minus 2 volts, producing a measurement range of around 3 to 7 volts, orders of magnitude greater than our original uncertainty. Such a reading would, of course, have no practical value. AEMC features instruments, including multimeters, that perform auto-ranging for automatically selecting the most appropriate range for the reading. This also illustrates the advantage of higher count instruments. For example, a 6,000 count multimeter can display 1,000 more readings than a 5,000 count model without changing to the next higher range. Since these 1,000 additional readings will have a lower per count unit value, they will result in a lower uncertainty. Before leaving this topic, we should point out the difference between uncertainty and error. Although the terms are sometimes used interchangeably, uncertainty represents the range within which the true measurement falls, while error defines the absolute amount that reading differs from the true value. Although it may seem initially counterintuitive, it would be easier to accommodate error than uncertainty, as all we would need to do is offset the measurement by the amount of the error to obtain 100% accurate results. Let's review a few key points we've covered. It's important to understand uncertainty specification to properly determine an instrument's accuracy. The lower the uncertainty, the higher the accuracy. Digits and counts define an instrument's resolution, but not its accuracy. When comparing performance, bear in mind whether the instrument's uncertainty is based on percentage of reading or percentage of range. Be sure to select the optimal range, generally the lowest possible, when making a measurement. And finally, higher count instruments can produce more readings with lower uncertainties than lower count instruments. We hope this will help you better understand and interpret uncertainty specifications and how they define an instrument's accuracy. This in turn will enable you to make more informed decisions when choosing the instrument best suited to your requirements. And be sure to check our YouTube channel for videos about other topics in electronics, including the many products offered by AEMC.